My name is Armin Ronacher, and I want to walk you through a little bit of our learnings on moving from a Python-only shop to one that processes most of our event volume with Rust. In a prior life, I've created quite a bit of open source software, primarily, I would say, in Python. I created the Flask micro-framework and quite a few other libraries in that ecosystem. And a couple of years ago, I joined a company called Sentry, where I focused, I would say, at least by time spent on this problem, quite a lot on pipelines, data pipelines, and event processing. Because if you summarize our business down, we're taking error, crash reports, performance profiles, anything of that nature, and really throw it into a complex pipeline that wants to then quickly show this data to customers. So I want to show mostly the learnings that we had with taking what is really Python-only code and bringing some Rust in, and what worked, what didn't work, and how we would maybe change some things. I will not bore you too much with what the product is, but I think it's worthwhile understanding the kind of problems that we're having. Originally, the business was primarily based on there's an error report, there's a crash report. We want to show it to you as a customer, and we want to aggregate it, which means that we need to analyze this report and at least detect that it's a duplicate or not. Along the way, in order for you to see a nice crash report, there's some extra information needs to be fed in. So for instance, in JavaScript, a source map needs to be applied. Or if you take a native event, it usually comes in as a memory dump or at least an unsymbolicated stack trace, and we need to apply dwarf or PDP debug information to actually make it readable. So a lot of the event processing involves a relatively complex and large debug information files. We also have replays. They also need to be stored somewhere. These are browser sessions that come with DOM captures. And then we have tracing data profiles. You get the idea. And a lot of these require quite a bit of extensive processing. And they can also get very large. And so we were originally just a Python shop. Everything was written in Django with Celery as the main way of interacting with RabbitMQ. And already in 2015, I believe, we started poking around with what we could do to optimize some of the slowest stuff that we had, which as the volume of JavaScript events was increasing over the volume of Python events that we had originally, it became pretty obvious that source maps are turning into some sort of performance challenge for us. So the choice of Rust to solve the problem of performance on source maps came mostly out of my personal interest in the language. So I already implemented the source map processor or the source map managing library in Rust, mostly just as a way to learn the language. And then independently of that, we discovered that performance was actually an issue on source maps. And I just took that Rust library. I used a library that we built called Milksnake, which allowed us to expose that to Python. And actually exposing that was very trivial due to a bunch of decisions in Rust at the time that made it very easy to make Rust available via FFI. So we had this library already as a toy. We just tried it in production. It actually outperformed the Python performance significantly. And so that was sort of the initial way in which that appeared. What is really nice about the way you can use Rust in Python nowadays in particular is that there's an entire ecosystem that has been created, because we were clearly not the only people that had a desire in writing extension modules in Rust. And so this is much easier now. And as a result, it's much more established to use Rust with Python. So it allows for very efficient code sharing between Python and Rust for performance critical code. Our use of Rust mostly comes down to being involved in a pipeline in one way or another. So we have an ingestion service, which is at the beginning. We have symbolicator, which is the heavy lifting for symbolication and for source map processing. And then we have a little bit of Rust code all over the code base through Python modules. This is modules where we expose functionality from our Rust libraries into Python. And the goal here is mostly shared code. And some of this is to only write code once. Another one is also that in some cases, some of the Rust crates are really quite nice. And they have certain performance characteristics that are also nice to have in Python code. So for instance, we use the Rust regex library because we can actually throw more or less untrusted regular expressions at this library that we couldn't do on the Python side, because there's no real way to sandbox a regular expression that sort of runs into a very non-performant exponential exponential backtracking. Did Rust work at Sentry? And I would say the answer is yes, very much so, and we would definitely pick it again. Nowadays, I would say the benefits are very obvious. I think at the time when we picked it, the benefits were maybe a little bit unproven. And the downsides were not that obvious yet. I think the downsides are very obvious now. I think there's a good understanding that Rust comes with a certain amount of developer overhead. You kind of know where the good and the bad tooling is. So for as long as the problem that you're having overlaps with the good tooling, we're really good. So it might work for you, it might not work for you. But what the argument I would make now is that whereas maybe 8 years ago when we first went down this adventure of using Rust at Sentry, a lot of it was unexplored space and unknown territory. And now this is, I think, largely understood by everybody. So you don't have to write months and months of a POC to figure out if it works for you or not. You can kind of look at the problem, you can look at Rust, and you can probably figure out within a day or two if it's going to be a good choice or not. I gave a talk last year at P99 CONF that goes into our processing pipeline, and I think it's worthwhile for you to watch it if you're interested in this kind of stuff. I want to just show you the basic overview of the pipeline so they kind of understand a little bit of where Rust is sitting and why it's sitting there. So we have the main Sentry service, which is the monolith. This is where most of the database shenanigans happens. And this is also where we have a lot of the processing pipeline where we go to symbolicator and services of that nature. The main ingestion system is called Relay, and it is called Relay because it can send into another relay, and at every point it goes through it, there's a hypothetical performance optimization it can do. Most of the work is actually being done by the first relay, which really is responsible for making sure that the customer that stops spending money will not send the data forward to the rest of the infrastructure, and it will also communicate to the clients that you're over quota and the client should stop sending. So there's a contract between an SDK and the relay to communicate rate limits. So if you're sending too much, you can throttle down the clients if the clients cooperate. So relay is the first point of traffic reduction. It also applies sampling. So if you are sending within the bounds of what is acceptable traffic, but you are sending above what the traffic is that we want to store, we might only retain, say, 10% of your overall events. And then for the rest of the events, we only retain aggregates. So Relay also does the aggregation part. That's sort of the idea. And Relay is written in Rust, and the bits and pieces of the Sentry processing pipeline further down are also written in Rust, primarily symbolicator. So I want to show you how we actually got Rust into this whole thing without too many major struggles. So as mentioned, we have to enforce quotas on Relay. We have to support geo-distributed deployments. We have to perform sampling, metric extraction, PI stripping, and data forward conversion. This is all known parts. And so when we first started doing this, we realized that it's actually very risky to roll this out all at once. So preferably, we can kind of side-by-side run things until we realize that this is matching behavior between what we had in Rust, what we have in Rust, and what we had in Python. So we sort of already knew at that point when we rewrote Relay that Rust is most likely the choice that we want to have. We didn't go too deep into alternatives. And part of this was the desire to, you have to think that at the time when Sentry was built, nothing really was that well specified. And it was an open source project, and it also already had a lot of external clients and customers sending their own data because we didn't have SDK support for the dedicated platform, which meant there was a lot of data coming in that we didn't quite know the shape of, and there was not a strong schema enforcement. So the idea really was like, if we write it in Rust, then maybe we can reuse some of this code between Python and Rust, and we can sort of side by side run the validation and see that the protocol matches. So originally, the store endpoint was written in Python. The goal really was to fully do away with that endpoint, write a new service in Rust, have the data appear there, send it via Kafka to Sentry where a consumer picks it up, and then throws in the rest of the pipeline. Originally, the store endpoint was really written with the idea that anything goes, so there was very little validation. There was a JSON load written in Python that uses the simple JSON module, and it just accepts whatever is there. It does a little bit of validation, but the validation was very limited. So we really didn't have any schema. There was very inconsistent behavior in the protocol. And because customers kind of sent the data on their own, we had more traffic and more data coming in than our test suite was actually covering. And we had also a lot of quirks in the protocol, like transparent pixel support to allow sending data in via image load tags, which was a thing at the time. When we wrote this originally, Flash was still around, so there was also support for cross-domain XML and stuff of that nature. And I would just summarize it was unreasonably lenient. And so we wanted, on the one hand, to capture as much of the existing protocol as possible, but we also wanted to nail down the protocol a little bit so that performance optimization was actually possible. If you think of writing a protocol, parsing a protocol in Python and Rust, you actually very quickly figure out that if Rust comes after Python, then you might actually have something supported on the Python side that no other language would ever support. And when we started using Sentry, which is the most commonly used JSON and serialization library on Rust, we discovered that we couldn't express everything in Sentry at the time. One of the things was that our protocol was incredibly deep, and we had rather low recursion limits on the Sentry side. This is because Sentry sort of goes recursively down. It actually keeps quite a bit of state on the stack. And because we had used quite a concurrent system, the per thread stack limit was quite low. But even with that, Sentry and it runs out of stack space, it more or less aborts the process. So we had to work on that. We also had the challenge that because our initial clients were written in Python, our initial server was written in Python, we used Sentry dump s and Sentry load s on both sides. JSON load s and JSON dump s on both sides. And they actually support a superset of JSON. So for instance, if you have not a number or infinity, they will actually be written into the JSON as an invalid nan or infinity, which is clearly not valid JSON, but it was out there. We had clients sending this. And we didn't really want to fork the Sentry parser for this, and clearly nobody wants to have this kind of support in the Sentry JSON system. So we actually just went over the incoming bytes, did a tokenization on top, and whenever we encountered a nan outside of a string, we would convert it into 0 with a bunch of spaces, and the same for infinity. That wouldn't make that valid. It would just show you a 0 where you kind of would want to see infinity instead, but it at least allowed it to parse. The bigger problem is that Sentry has a quite limited data model. We ran into this a couple of times, for instance, because we wanted to represent meta information in the JSON stream for parsing errors, because our protocol we didn't want to reject the entire payload. We wanted to reject individual bits and pieces further down the structure, but then retain meta information that there was an error on that level. And Sentry makes it very hard to pass state through. And the way some of the Sentry libraries get around it is that they use inbound signaling for encoding state into a temporary object, for instance, passing that from serializer to the sort of the callbacks that work on it. So there was a lot of this. We are still using Sentry, but we have quite a bit of extra infrastructure on top to make it work. The inbound signaling here, for instance, is that if you use JSON as a library or as a protocol, you can opt into what's called arbitrary precision. And Sentry in itself doesn't have a way to represent in its data model things that are not native to the Sentry data model. So for instance, the Sentry data model has uint32, it has uint64, it has like all of those types, but it doesn't have one for arbitrary integers. And so the way the serializer gets around it is that if the deserializer encounters a number that's too large and arbitrary precision is turned on, it will actually emit tokens that represent an object. And the code that's generated later to parse, for instance, a U128 out of an arbitrary precision integer will actually look not just for a token or like a Sentry value for an integer U64, I128 or something like this. It will also look for this object. And this also means obviously now that if someone were to send in on a positional data stream where this large integer would be expected, this object literal will become part of your API. So this inbound signaling we kind of still rely on in a bunch of places, but it makes me very uncomfortable, and I wish there was an alternative to this. One of the first footguns that we ran into, and I think there's a footgun that we keep running into, is that when you profile something, memmove might show up very quickly. And this is because some of the patterns that are quite fast and common in another language accidentally turn into very slow in Python, in Rust. One is huge return types. If you have an error type that is a little bit too large, it increases the cost of every function call. The second one is that strings in particular, you might clone quite a bit in Rust, where in other languages you might just do a pointer bump or maybe a ref count increment or something of that nature. The first one here, this is an example from Mini-Ginger, which is a templating engine that wrote in Rust. Originally, this error type really only had two fields, and it was called kind, error kind, and detail, which was a static string at the time. And that was a struct. And I passed this down from place to place, but over time, more and more debug information was added to this error type. So the error grew in size. So it grew from what was probably 3-4 words to maybe at the end, like 30 words or something of that nature. And I didn't really look into like how much slower it was going. I just realized at one point, hey, this is like if I profile this is a lot of memmove going on, and or clones in general in this case. And it actually really turns out that when I just started boxing the contents of that error, so I still returned error in places, but I boxed, which means I make a heap allocation for the actual data in the error. I want something like 20-25% performance overall on the benchmarks, which was significant. So that's one of the things that we also discovered in Relay, is that you can very easily write code that is not really a zero-cost abstraction, because the compiler is not entirely able to optimize some of those cases, particularly when it comes to map, unwrap, things of that nature. This is a hilarious version of this, where the original code was really providing an API that made it sound like you're kind of reusing strings all the time, but in reality, somewhere in here, there's a clone hidden. And what it basically meant is that when we processed source maps, for every single token that we were manipulating, we were also updating the source reference that it was pointing to. And if you would write this in Python, you wouldn't really notice anything, because you would just assign one string to a place of another string, and there would just be a ref count increment. Because of the way we created this API, it was kind of hidden that behind the scenes in add source, I think add source, a clone of the entire string was happening. And so when we applied offsets to n tokens, we actually performed memmove over n bytes of source string n times. And so when we fixed that, and we didn't catch this in our regression tests, because like all of the inputs were kind of small, and that really was only noticeable when you put like a megabyte, 2 megabytes of data into, or even 10 megabytes of data into sort of the update loop, where all of a sudden you realize that, well, this was in a milliseconds before, and now all of a sudden it takes a minute. So these kinds of errors can creep up, and we had them a couple of times. When you want to write a web service in Python, in Rust, you have to kind of pick the base on which you put it. Originally, you put it on the old Tokyo system together with Actix and Actix Web. It looked very appealing, and I think it mentally still very resonates with me to build on an actor framework. But we found it incredibly hard to manage back pressure in the system. And over time, what we have created became quite a bit of a mess. So we went through a couple of iterations, and today we have a custom service layer. It mostly uses async await. It uses Axum as sort of most basic HTTP system they can have. And we basically have much more explicit management of back pressure in the system. We accomplish this mostly by using channels very carefully and reducing the total amount of stuff in flight at very specific points. In Actix, you have basically mailboxes between all the actors, and they're kind of unbounded. And even if you were to ever run into the size limit of a mailbox, you can't really await it anywhere. So you can't exert back pressure throughout the entire system. So we found this much easier to do with just sitting on top of Actix. The last thing I wanted to mention is when we originally exposed Python code to Rust, we did it with a library that we built called Milksnake, which allowed us to compile shared libraries into Python-independent shared libraries that we were able to load with CFFI. That was done so that we can target both Python 2 and Python 3 at the same time. Nowadays, we only have Python 3 and we use the stable ABI, which allows us to compile against one version of Python, and it works in arbitrary versions of Python from that stable ABI version onwards. And so that means that you can now use a library called Pyo3, which is very convenient to export Python 3 Rust code to Python 3. We use this not yet at Sentry in the form that I wish, but it does show up already in some of the newer code. It uses Maturin, which is a tool to create and distribute wheels. And it provides a very convenient way of managing the GIL and doing borrow management. And it actually makes it really easy to write Rust code to Python now, much easier than before. So what maybe took us like a day or 2 days of CI setup and just the building around and the PyPI setup, you can now basically do most of this within 10 or 15 minutes because Maturin does such a good job at creating the developer experience around it. And this is really our story of getting Rust into Sentry. Overall, I think it was a really good choice. And I think that there are many more companies that could benefit of this, particularly in languages where there's sort of a general performance challenge involved. I think Python is a very obvious one. JavaScript still shows up in a bunch of places being a performance challenge. But we also found it incredibly helpful just when you distribute things. I didn't go through this in this talk, but we wrote our command line utility in Rust. We can compile it for different platforms. It runs everywhere once it's compiled to it. It doesn't have any crazy dependencies. And this means that every single SDK that we have, they actually also pull in the a Rust binary behind the scenes to, for instance, upload large files, debug information files to our API. And yes, it is a binary blob, but I think overall for us, it has worked really well. So thank you very much.